Our next speaker is Christopher John Sharpe. Christopher works in the data acquisition team at the Diamond Light Source as a software engineer. He has been responsible for designing and implementing the software to fully automate the VMXi Beamline at Diamond, and it has been successfully deployed. He will give us a talk titled A Software Architecture for Beamline Automation, VMXi Use Case.
Morning. Yes, my name's Chris Sharpe, and as I said, I work in the data acquisition team at Diamond Light Source. So my talk is on how we actually managed to automate a Beamline, but not changing the data acquisition software at all, which is a challenge too much. So there are several MX Beamlines at Diamond, and back in 2013, IO2 was selected for phase 3 for an upgrade, major upgrade, to become VMXi, and that's specialized to process these crystallization plates here. And so in these crystallization plates, you have a well, or within that well, you have a crystal sample of some biological material, and then you just create diffraction images from there. And of course, you can generate a great deal of volume from one plate as well. So the actual end station went through a major rebuild here. So this is it shown without the actual, the mini hutch here, the radiation shielding. The main features are the storage units that contain over 750 plates each. So users will send these plates to Diamond Light Source. So there's a tremendous amount of plates here. Within this mini hutch, you have a local storage area that has up to 12 slots of plates which are ready to prepare to be processed in the Beamline. And you have a data collection environment where the actual plate data is collected on an individual plate. So major challenges, major differences, there's no direct user interaction with the Beamline at all. So users will work offline through a web interface here called SyncWeb, and they have an image of their crystal sample in a well, and then mark where they want to collect data, and set up the data collection parameters for a plate. Then this is persisted in ICALEPCS, which is a database designed specifically for MX pipeline, experiment pipeline. And at some point, GDA, the data acquisition software, would then process this plate as well. So that's a challenge for us to do that. It's automated. So GDA, in effect, would need to do this repeatedly, indefinitely, and very importantly, robust defaults. So otherwise, it's not an automated system. So in effect, GDA has become a plate processing machine. So we talk about automation, and then this is the domain of AI. This is where we look for our models and our architecture for automation. So any AI architectures have these three capabilities. They need to sense, plan, and to act as well, to enable an agent to act autonomously within its operational environment. So we've got to work out, given that sense, plan, and act, where does this lie in terms of VMXi and automation? So our plan here, as I said, the data collection experiments, they're stored in ICALEPCS. So that's great. So we know that tells us exactly how the Beamline should set up and how it should for data collection. Now the other issue we have all these plates in the storage units. So how do we select one of those plates, just one of these plates to be loaded in onto the local storage area? But then, of course, this is quite a computationally complicated task to do this. But in the end, GDA doesn't really care which plates, how this actually selection process happens. All it cares about is that it just gets that one plate to be loaded into the local storage. So we can kick that out, make that an external process. So if we've got these two elements of the plan, we know they're external now. That's great. So that just leaves us with the sense and act to wire together. So this is a well-known architectural model, which is just a reactive controller. So basically, from what we sense. This is then we perform a direct action from what we sense within an environment. Now, so these are the attributes to this type of model as well. And the most important is it's stateless, which means if there's a problem, or say we have a catastrophic failure, it doesn't care, it holds no state. If we bring it back up again, it should behave exactly as it's done before, just purely based on sensing the current state as well, and it performed the action based on that as well. So we have two agents here. One's to do each task for the automation. So a sample handling agent and a data collection agent. Now the loop here, so what we have here, the loop here actually defines the classic thing of the reactive controllers. So it loops time t, and then it just processes the sense and act capabilities in order as well. Now, how do the agents know what to do? Well, there's no boss at all. There's nothing actually telling the agents what to do. Instead, we have a central information source through which the agents can communicate. And all they need to know is the plate state to actually determine which action to take. So this plate state consists of the location of the plate, and also whether it's been shot or not, whether it's been exposed to X-rays. So that's all required for this communication here as well. So this information, of course, is a attribute of a plate, and that's stored in ICALEPCS as well. So that's where we get our information from. So what we see here is that all the states that the plate can be in at any one given moment in time. And so, for example, here, one thing to mention as well, so the sample handling is just responsible for updating the location of the plate, while the data collection is just responsible for updating the actual shot state of the plate as well. So, for example, if we had moved a plate from local storage onto the goniometer, the sample handling would change that state, and then the plates would be on the goniometer, and that would be the trigger, the perceptual cue, as it were, to the data collection to go off and do a data collection. So there's no direct communication. It's just purely through the state here that these two agents are able to synchronize and coordinate their actions together as well. Okay. So let's go through each agents in turn as well. So our sample handling, our basic goal is to convey plates, okay, from the external storage to the goniometer, from the local storage to the goniometer and back again. So for that, we have 4 high-level PVs for each one for our particular endpoint in that journey as well. But the thing is, we're still left with an issue: is how do we select which action do we select at any one given moment in time? So for the sample handling controller, it's an adaptation of Rodney Brooks's from MIT, who's a former synchron behavioral robotics, his subsumption architecture to actually resolve this. So tell me which action we should actually take from these 4 PVs. So that's the design of the controller here. So we have there's a hierarchy of behaviors as well. So the top level behavior is a higher level behavior and the lower level behavior. So again, we want to make sure we move our plates safely from one point to another as well. So robustness, if we detect any problems or any issues as we're doing the move, that we're able to handle that and deal safely with that particular issue at all. Well, the sample conveyance is to do with moving the actual samples from one point to another, so all the plates through here as well. So what happens, sensor input is fed into the behavior layers in parallel. If the sensors are stimulated, and the behavior layers are said to be fired, which means that they generate an action depending on so there's a finite set of actions. So it's basically a set of if-then rules, and one action will be generated from from a particular behavior layer. Now, if these 2 behavior layers are fired together, then the higher level behavior will be its action it's generated be selected over the lower level behavior as well. So this is what the S is here, that's suppressing the output from the lower level behavior here. and then it's presented to its action executor, and then its action is then acted upon there as well. So in terms of the sample conveyance, so what do we have here, the sensors? We have load plan, which we discussed, which is just the barcode being sensed, and then the plate state from I/B. So these two things have been fed in to the behavior layer. And we have just obviously got 4 actions, so we just have 4 rules, right? Then deterministically, so we sense that particular state. So there's the hierarchy of rules as well. So we just select one of those actions that are presented to us. Now, interestingly enough, if you rearrange these actions, the rules, you actually have a different kind of emergent throughput behavior as well. And then the action generated, presented to the action executor, that executes the action on a separate thread, and then it inhibits any sensor output here. So in other words, we only want to perform one of these actions at a given moment in time. Okay, let's moving on to the data collection environment. So our goal of data collection obviously is just get diffraction images from the plate. So here is the data collection environment. The main thing is fast shutter. We open the fast shutter. We expose the plate, which is on the goniometer, to X-rays, and then we acquire data from the detector. So that's our goal, is just to collect data on the plate. So the high-level algorithm designed by the Beamline staff, and this is just an implementation. Each control layer there is an implementation of one of the steps in their algorithm, and here what we actually do is a sort of tasks within those particular control layers as well that we execute in order as well. So, as we said before, the cue to starting all of this off is just, if the plate's on the goniometer, it's not been shot, right, let's go off and let's do the data collection. Now, the first thing we must do is get all that information from I/B once for a particular plate. That defines what the experiment is, how the beamline should be set up, et cetera, and then we just simply move through the control layers here. Now, one very important point is on robustness as well. Before we do this, we must determine, ask a simple question, can we use the resource that we need to do this data collection? So there's many internal, external resources that we use. So for example, if the beam has gone down, then there's no point doing this at all. So that's our robustness here. So we ask that question every single task we have, can we use this resource to do this particular task? So we work through the control layers to move to a well. Now, interestingly here on the image matching, so what happens is the crystals may move, when they're being transported, they may be grown. So we may have a mismatch between what the users originally marked and what is actually in the crystal now. So we have to do a process of image matching. This is a computationally intensive task, okay? So according to our model, we kick this out. We don't do image matching at all internally at all. This is something that is done as an external service. So finally, after we've moved to well, then we're going to fire the X-rays at one particular crystal, particular point of interest or region of interest. We come to the scan manager, then we collect sample data. So, but again, this is very complicated because we're coordinating the movements of the stage, and we're setting up the detector, opening the fast shutters. That's a complicated synchronization problems to solve. So we don't do this. So very fortunately, we have the mapping project. You may have seen posters around this already at Diamond that's been deployed across beamlines there. And we use that to do the synchronization. So all we do is just present the hardware with our experiment parameters, and we press go, and we just monitor the actual progress of this. And of course, if there's any problems, then we deal with that as well. So eventually, we process the plate, and then we set the state the plates are being shot, and that's the cue then for the data for sample handling to remove the plate from the beamline. So this is the architecture overall here. So the top level here, as we said, we have our information source and services, a load plan we talked about, the I/B, an image matching which we kicked out. So in GDA, we just have the two data collection agents and sample handling agents. Very important aspects of this is communication breach. That's a very important part of this. I'll just quickly say as well, this comes really cheap, right? It's about just under 3,000 lines of code for the raw controllers as well. So, it's not proportionally difficult for supposedly complex tasks to do this at all. And then we're still hooked into the EPICS layer here to issue PVs, set PVs down to the EPICS IOCs. So yeah, we haven't compromised GDA at all. So we're using exactly the same tools for the actual, to do this, to do automation. Summary, so automation is possible with standard software tools. AI is our domain solution, right? Planning and decision making, kick them out. Computationally intensive tasks should be external. And hardware synchronization, push down to controls layer. And the reactive agents, all they do will initiate and monitor actions only. Tremendous amount of people to thank here who are involved in this whole project. And thank you for your attention. And any questions, please?
Okay, thanks for the presentation. I have a question about if you have any number about the succeed rate of the image matching recognition that you use.
Yeah, that's a good one. Yeah. Depending on the plate type, so you have different plates, manufacturers as well. So at the moment, just for grinder plates, and that's been relatively. It takes lots of calibration, and it's pretty. We got it pretty good now. Actually, we're pretty high in terms of doing the image matching as well. We're still doing that for different plate types to actually get the image matching good. Yeah.
Is there any other question? I had a small one.
Yes.
Do you plan also to do this automation for pins or only for plates? So the sample mounting and...
Oh, so for pins. Okay, yeah. That's quite a live topic in Diamond. So we're still using the old GDA, and they have an in-memory queue for that as well. So actually, but yeah. So this is a complete departure from how it's done at the moment.
It's only for plates.
No, it's completely adaptable, right? It's just follow the same model, and it's relatively simple. But you're dealing with legacy, right? A legacy code, so it's whether, yeah, this will work. It will work.
Well, but then you will have to manage the mounting failures and...
Yeah, exactly. The robustness is absolutely crucial element to this. Really, really important. It's quite good because you actually push all the, dealing the things you said. You're just purely monitoring. You're just making sure that you're handling just the problems, and that's it as well. But that's difficult, very difficult to actually. Yeah.
Okay, let's thank the speaker again.